Welcome to the next step of selecting the best test. In this recording, we'll be looking at a variety of different examples of how to actually word the different tests that we filled in on this graph, from Pearson correlation and simple linear regression all the way down to logistic regression. So let's go ahead and take a look at a couple of examples that you already are familiar with. And these are the chi-square tests that you've done previously. The first one says you'd like to evaluate whether men and women are equally represented in the population, in other words, 50% each. And so as I'm doing this, I think, okay, here I have a variable, men and women, that's gender, and it has two categories, so that makes that dichotomous. And so I'm going to type that in here. Actually, why don't I copy and paste it? That will make it more visual. Okay, so here we have our dichotomous variable, and when I say equally represented, it could be that we chose something else, not 50% each, but it could be 40-60 or 20-80. We know that in some populations like the VA, it's not necessarily 50%, but this just says equally represented. This is some kind of expected value. So here I have a dichotomous variable and some kind of expected value, and I would go to my table here and I would say, okay, here I have dichotomous and an expected value, and that means I'm going to do a chi-square goodness of fit test. So that's as easy as that. And I'll just abbreviate it there since this is a review for you. We would do the same test if we were looking at something that was nominal or ordinal. The chi-square goodness of fit test really fits with any of those. The next example here, it says you'd like to evaluate whether gender is associated with diabetes. We've looked at something similar to this in your assignment already. And here we have gender, which has two categories, female and male. So again, we want to identify that as being dichotomous and is associated with diabetes. No diabetes, pre-diabetes, or diabetes. And so that sounds like it's an ordinal scale with limited values. We'll just copy the ordinal part. Well, we copy the whole thing. Okay, so here we have our ordinal variable. And because we have dichotomous by ordinal, then we would go here to our dichotomous row, and we go over here to ordinal. And either way, even if you start with ordinal and go to dichotomous, or you start with dichotomous and go to ordinal, all of those possible scenarios where we have two categorical variables, this is going to be your chi-square test of independence. So we have these two examples from what you've learned in the past, and you can see how you use the table here. If you happen to have dichotomous by dichotomous, then that would be the one situation where you could use a Fisher's exact test. Otherwise, the chi-square test of independence would be the one, if you have two categorical variables, would be the best test to use. Okay, so let's go ahead and scroll down. And we're going to look at a couple of other ones here. And this is our first one to evaluate. And you'd like to evaluate whether blood sugar is associated with cholesterol. And so if we think about blood sugar measured in milligrams per deciliter, that's going to be an interval ratio variable. So I'll go ahead and put that here. And if we have cholesterol also measured in milligrams per deciliter, I'm going to try to copy it without the carriage return. That's also interval ratio. And so here we have a situation where we have interval ratio by interval ratio. And so the test for that is called a simple linear regression. I'll spell it out this time. And the interesting thing about regression, and you'll hear me talk about this in the future, is that a lot of the other tests really are the same thing mathematically, but we give them a slightly different name, just because that helps us understand more about how that test operates. Really, all of these tests up here on the top row are mathematically very similar to each other, and we can run, for example, an independent t-test as a simple linear regression. But we still call them different things because it gives information to our audience about exactly what we're doing. So here we have our two interval ratio variables, and that is a simple linear regression. If we're looking at the correlation part of that, that's called Pearson. Correlation. And so those two things really are mathematically identical. They just give us a different look at the different things that we're measuring. So here we have an example of our simple linear regression. The next example is about looking at whether men and women have the same average cholesterol. And so here we have our men and women, our gender again. So I'm going to go ahead and copy that. Anytime we see something that has two possible categories, we can just automatically put dichotomous in there. And we want to know if they have the same average cholesterol. So let's take a look at this variable. Cholesterol has this thing we consider sort of like a flag. It's the units that cholesterol is measured in, milligrams per deciliter. And so we say that's going to be interval ratio. And so I have a dichotomous by interval ratio. And you'll notice that there are a couple of different places in the graph where those two intersect. Here we have our interval ratio, and there's dichotomous, and so it tells us this is an independent t-test. Typically we like to think of it this way with whatever it is that interval ratio is kind of like our main variable that we're looking at. We'll look at the scenario where we have dichotomous here and interval ratio, and notice how it's grayed out. That's because that's not typically the way we would normally operate with that. So look for one that has a test that has an option for that. So this is a dichotomous by interval ratio, and so that is going to be an independent t-test. And we'll learn more about what t-tests are and what Anovas are in the future lessons, but for now, just knowing that that's what that's called is an independent t-test. So let's go ahead and scroll down to our next couple. Here it says you'd like to evaluate whether people living in 3 towns, town A, town B, and town C, and I hope that strikes you as being nominal. Let's see if I can capture just that. Here are our towns, our nominal variables in our towns. We have 3 different towns, so it's not dichotomous. They are not necessarily in a specific order, so we'll just call that nominal. Have the same average cholesterol. Now up here we already decided that cholesterol in milligrams per deciliter is interval ratio. So let's go ahead and copy that here. As soon as we have something that has more than 2 categories by an interval ratio variable, then that test is called a one-way Anova. You can see that here, that we have that. So that's our one-way Anova test. These two, again, are very similar to each other. The dichotomous is just a special case of a categorical variable that only has 2 categories. And so it is simpler mathematically, and it doesn't involve quite as many possibilities in terms of writing the null hypothesis and things like that. So all of that you'll be learning very soon. Our next 2 tests really are kind of looking at, again, 2 things that are similar to each other, just like our independent t-test and one-way Anova are very similar to each other. The one-sample t-test and the paired t-test are very similar. So let me read this one. For a group of people who enter a lifestyle change program, you'd like to evaluate whether their cholesterol at the end of the program, again in milligrams per deciliter, is different from their cholesterol at the beginning of the program in milligrams per deciliter. So here we have cholesterol at the end, and that is interval ratio. And we have the same thing that we're measuring. We measure cholesterol at the beginning, so that's also interval ratio. And you'll notice that this kind of looks similar to what we did here with simple linear regression. And this is where I need to point out an important difference. If you're measuring the same thing, here we have cholesterol, both at the beginning and end, then it's more powerful to use what's called a paired t-test. It adds in something that allows you to use the relationship between where somebody started at the beginning and where they ended up. And so we like to use a paired t-test whenever we possibly can. It usually means that we don't need as large of a sample size later on in terms of our study design, so it has some efficiency there. So because this is an interval ratio for both variables, see how it's the paired measurement? So in other words, it would be the same before and after. It would be interval ratio before and interval ratio after. Then this is called a paired t-test. So you'll start seeing that we're doing lots of t-tests here, and t-tests are one of the things on your competency list. The next one is very much related to a paired t-test, and this is where you'd like to evaluate whether the average cholesterol, so we keep coming to the same variable, for a particular group of people is equal to 180 milligrams per deciliter. And so here we have cholesterol, and again, it's a interval ratio variable. And this 180, I hope this is familiar to you. Here we have some kind of an expected or reference value. And so let's go ahead and use that same terminology down here. The 180 milligrams per deciliter is what we're expecting or what we're comparing it to. Expected or reference or comparison value, those would all mean kind of the same thing. And so instead of comparing it to somebody's cholesterol at the beginning of the test, we're going to compare everybody to this same standard of 180. And this test is called a one sample t-test. So here we have several different t-tests, and you'll notice that we have an independent t-test, we have a paired t-test, we have a one sample t-test, and all of these different t-tests are just for different scenarios. So it's important if you're talking about t-tests that we designate, oh, that's an independent t-test, oh, that's a one sample t-test, that one's a paired t-test. These tests have other names. For now, I want you just to learn those names, but when we go over them individually, I'll tell you what the other names for them are that you might see either in the medical literature or on a CPH exam or sometime in the future. Now, I'm not going to go into all of the details of multiple linear regression or logistic regression, but I've given you an example here of what each one of those would look like. And basically, you're taking the same exact scenario that we had above, but then you're adding more variables to whatever it is that we're looking at. And so remember how here we said for the multivariate, we're looking at multiple predictor variables for whatever the outcome is. And so here's the scenario that we had above for an independent t-test. You'd like to evaluate whether men and women have the same average cholesterol. And here's the multiple part. When correcting for age, race, ethnicity, smoking status, and blah, 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 whatever other variables you might be interested in that you might think are valuable for that analysis. The main difference with logistic regression is not that you have extra variables, but it's what is your outcome and how is that coded. And so here, you'd like to evaluate whether men and women are equally likely to have diabetes. Diabetes is a yes-no as we've classified it here. And so that's a dichotomous outcome. See how this lines up with the logistic regression. Logistic regression has a dichotomous outcome, whereas multiple linear regression has an interval ratio outcome. You'd like to evaluate that when correcting for, and these could be any correction factors. It could be things in the medical literature that you know impact that relationship. It could be other variables that you collected that you're wondering if they have some kind of a relationship. And so there are a variety of different reasons that we might correct for or adjust for or add other variables into the mix, basically. And so we'll be talking more about these in the future. It's not important what those extra variables are, it's just that we have them. So there's not just the one predictor, which is dichotomous, nominal, ordinal, interval, or ratio of the outcome, but there are multiple predictors, and usually or very often those are phrased as correcting for or adjusting for other things. And so that concludes our video. For now, the main thing that you need to remember, you're going to be taking a quiz. There will be a variety of different possible choices, and you can take the quiz multiple times. Each time you take it, you'll get different questions. So even if you get 100% the first time, I'd encourage you to take it multiple times, just so that you get extra practice. You're going to need to read a sentence, and then the first step is to figure out what kind of variables you have. Is it dichotomous, expected value, ordinal, nominal, interval, ratio? And then only once you've decided what those variables are, you're going to select the best statistical test for that particular situation. And these are the only ones that you're going to have to choose from. You're welcome to use this graph while you are taking the test. I encourage you to do that. Simply put your finger on one variable and follow it across and figure out exactly what kind of test that could be. One of the hints that I always give people is if an interval ratio variable is part of that combination, if there are two variables and that kind of thing, if interval ratio is part of the mix, then stay right here on the top row. That's just going to be your best guess, and we'll learn more about why that is as we go through the different statistical tests. The last caveat, and I forgot to mention this when we went over this table earlier, is that there are some exceptions to this table. It doesn't capture every possible combination of variable types. Clearly, we didn't fill in some of the shading where there are actually tests. There's a test here that we didn't talk about that you're not required to know about. Everything in life doesn't neatly fit into little cubby holes. And so this really is a really good starting point for how to think about the different tests. The other thing is, if there's another way of thinking about picking the right bivariate analysis, there are flowcharts, there are tree diagrams, there are other kinds of spreadsheets that you might be more familiar with. You are more than welcome to use those. They should come up with the exact same answer for the very basic examples that we'll be having in this particular class. So if you find something that works well for you, please share it with me. I have several other examples that people have shared with me that I'll be sharing with the class that hopefully will help people find one that works really well for them for studying. If you find one, then keep using that. The more you use it, then when you get to a scenario where you need to figure out the right test, or it tells you it was an independent t-test, then in your mind you will be thinking about exactly what that means much more easily if you use that table or that flowchart or whatever on a regular basis. So I encourage you to find something that works for you, and this is just one method that I found works for some students. So good luck on your quiz. Please take it multiple times, and I look forward to seeing your learning in this area.